Welcome everyone. Today I want to tell you a bit about geoinformatics and how we can use it to analyze satellite data or satellite images. As you probably know, geoinformatics is like informatics, but for working with geographic data, also called spatial data. Spatial data are any data that have geographic coordinates like latitude and longitude and can be linked to specific places on the Earth's surface. Spatial data refers to information about the location and shapes of physical objects on the Earth's surface. This data can also have additional attributes such as elevation, land use, and other environmental factors which help in analyzing the Earth's surface in various contexts. This data help with many different tasks, from mapping areas to assessing natural disasters and climate change. So, geoinformatics is the science that deals with collecting, storing, processing, analyzing, and visualizing spatial data. At the heart of geoinformatics are geographic informational systems, or GIS. I like the following definition of GIS. GIS is the system of hardware, software, and procedures designed to support the capture, management, manipulation, analysis, modeling, and display of georeference data to solve complex planning and resource management problems. GIS allows to combine different types of data, for example, data about terrain, vegetation, or climate, to analyze them and create maps. GIS play a key role in studying how human activities affect the environment, especially during conflicts, where it's important to get data quickly to assess damage. Later, I will tell you about some popular GIS systems that I often use in my research. These systems help me analyze the environmental impact of the war in Ukraine. This slide shows the classification of GIS based on 5 main criteria: purpose, problem orientation, territorial coverage, data organization method, and data access. GIS can be multi-purpose and specialized, then can be used for informational tasks, monitoring, inventory, research, decision making, as well as for educational and publishing purposes. Regarding problem orientation, GIS can focus on solving specific problems such as ecology, cadastry, geology, engineering networks, emergencies, navigation, transport, archaeology, and business. GIS vary by coverage, from global systems that cover the entire planet to national, regional, and local systems used at the level of specific municipalities or enterprises. GIS can be raster, vector, or combined. Vector systems use points, lines, and polygons, while raster systems represent data as pixels. Some systems may use three-dimensional data for more detailed analysis. Access to GIS can be organized in different ways. Global systems are available through the internet. Corporate systems are for specific organizations, and group systems can be accessed in local networks or personally. This classification helps us understand how and where GIS can be applied, which is especially important in the context of analyzing ecosystems and assessing the impact of human activities on the environment. Vector and raster data are two main types of geodata, and they have different features and uses. Let's start with vector data. Vector data is based on geometric shapes. There are 3 main types: points, lines, and polygons. Points represent single objects on a map, like the location of a village or a building, and they are defined by their coordinates, such latitude and longitude. Lines shoreline objects like roads and rivers, and they consist of serious points. Polygons are closed shapes and represent areas like land borders or lakes. Vector data also has attribute information. This means you can link extra details to each geometric shape, like a name, type, or area. This makes vector data very useful for analysis because it helps us not only see objects on a map but also study their characteristics. Now let's talk about raster data. Raster data is like a grid made of pixels where each pixel has a specific value. For example, in a raster image, the color depends on the RGB values, and in digital elevation model, it shows height. Raster data is defined by its resolution, which tells us the size of the pixels. Smaller pixels give more detailed images, but need more storage space. It's important to note that raster data can have one or more channels. One channel can show black and white image, while three channels can show a color image that represent different aspects of data. These features make raster data very useful for analysis, satellite images, and data from remote sensing. Examples of using vector and raster data are also different. Vector data is often used to create maps that show roads, rivers, and other objects. It's great for modeling special relationships between these objects, like the distance between buildings and roads. On the other hand, raster data is used to analyze satellite images. It helps us assess changes in land use, such as turning farmland into buildings, and create digital elevation models to analyze height and slope of the land. In conclusion, it's important to understand that vector and raster data have unique features and are used in different areas. Knowing the basics of each type helps us choose the best methods for analyzing and visualizing geographic data. Geographic coordinate systems and projections are important concepts in geography and GIS. There are many different coordinate systems used around the world. Each system helps us find the location of points on the Earth's surface. The most popular and widely accepted geographic coordinate system today is WGS 84, or World Geodetic System 1984. It's commonly used in GPS and other navigation systems. WGS 84 makes it easy to share geographic information globally. However, there are also regional coordinate systems developed by different countries for their areas. For example, in Ukraine, the coordinate system Pulkovo 1942 is suitable. A geographic coordinate system uses a spherical model of the Earth, usually with latitude and longitude. Latitude measures how far north and south a point is from the equator, while longitude measures how far east or west a point is from the prime meridian. But when we want to analyze the spatial data, we often need to convert these coordinates into metric systems like meters or kilometers. This is where projections come in. Projections are methods used to convert the curved surface of the Earth into a flat map. Different projections serve different purposes and can help reduce distortions in area, shape, distance, and direction. For example, the Mercator projection is often used to navigation because it preserves angles and shapes. However, it distorts the size of land areas, making Greenland look much larger than it really is. On the other hand, the Robinson projection provides a more balanced view of the world, making it suitable for general reference maps. Another important projection is UTM, or Universal Transverse Mercator, which divides the Earth into zones that are 6 degrees wide. Each zone has its own projection, allowing for more accurate mapping of small areas. UTM is often used in cartography and land measurements because it preserves size and distance within each zone. To work effectively with spatial data, it's very important to understand which coordinate system and projection are used. When analyzing data from different sources, all data may need to be converted to the same coordinate system and projection to ensure accuracy and consistency. In conclusion, understanding geographic coordinate systems and projections helps us analyze and visualize spatial data better. By using the right projections, we can represent our data in a way that makes sense for our analysis and decision-making processes. Well, let's talk about the two most popular geographic information systems, ArcGIS and QGIS. Let's start with ArcGIS. ArcGIS is a powerful commercial platform for working with geographic information systems developed by Esri company. It provides tools for creating, analyzing, and visualizing spatial data. In the latest version of ArcGIS, new features have been added that make it easy for many users. ArcGIS Online is a cloud-based solution that allows users to create, share, and manage maps and data over the internet. This is convenient for collaboration as it enables multiple users to edit maps and exchange information in real time. The platform supports both vector and raster data and offers many analysis tools, including geostatistics and modeling. With Model Builder, users can visually create geoprocessing models, making the analysis process clearer and easier to understand. On the Esri websites, there is a lot of technical documentation and training resources that help users learn about different features of ArcGIS. The user community actively shares experiences, allowing users to find solutions to various problems. QGIS. QGIS is a powerful open source software for working with geographic information systems. It's developed with the help of a large community of developers who constantly work to improve the software. Every year there is QGIS user conference in different countries and cities where new features and achievements are discussed. After each conference, a new version of QGIS is released, named after the city where the conference took place. In 2023, I was lucky to attend the conference in the city of Hertogenbosch in the Netherlands. QGIS offers many plugins that extend its capabilities. Currently, there are over 300 and more plugins available that allow users to add specific functions and tools for solving various tasks. In terms of functionality, QGIS is comparable to ArcGIS, offering a wide range of tools for analysis and visualization. However, it's important to note that the technical support for QGIS is not as developed as for ArcGIS, as a description of each plugin is the responsibility of its developer. This means that users may need to put in more effort to learn how to use specific plugins. In this slide, we compare to popular ArcGIS. ArcGIS is commercial software. It focuses on its own solution and data formats. This can limit users, especially those working with different types of data. On the other hand, QGIS is free and open source software. It supports many data formats and easily connects with other free resources. This makes QGIS a more flexible tool for many users. ArcGIS provides good technical support and extensive documentation. Users can expect help from specialists ready to answer their questions. This makes ArcGIS a convenient choice for those willing to pay for license and support. However, QGIS has an active community. They constantly work to improve the program's features. QGIS also supports different operating systems like Windows, MacOS, and Linux. This allows more people to use this program. ArcGIS offers good features for 3D modeling. However, working with special database may require extra software. In the end, the choice between ArcGIS and QGIS depends on your needs. ArcGIS is better for organizations that value technical support and integration with S3 products. QGIS is a great option for users looking for accessibility and friendliness to various data formats. In my research, I use remote sensing data. This is information about the surface of our planet obtained using satellites and other aircraft that capture images and collect data from space. In this lecture, I would like to avoid the complex technical details and focus more on the results of satellite data analysis. However, it's important to note that satellites are more than just cameras in space. Satellite data is collected by sensors on satellites. They are sensitive to specific ranges of wavelengths of light, known as spectral bands at specific times and from specific geographic areas, referred to as special temporal data at a particular resolution, meaning that one pixel corresponds to some geographic area with units like meters per pixel. Satellites repeatedly capture images of every location on the planet, allowing us to see how places change over time. For example, Sentinel-2 satellites pass over locations at least every 5 days, while Landsat satellites pass over every 16 days. Particularly valuable for analysis are high and ultra-high resolution satellite images less than 10 meters per pixel. To make satellite images suitable for analysis, they must be specially processed, such as by performing atmospheric correction. But even if you are not a geoinformatics specialist, you still have access to already processed high-resolution satellite images on platforms like Google Maps and Google Earth. After launch, a satellite is placed into one of several orbits around the Earth. Different types of orbits affect coverage and the speed at which satellites travel around the planet. For example, low Earth orbit, or LEO, located at an altitude of 160 to 1,500 kilometers. Satellites in this orbit move quickly and can can circle the Earth up to 16 times a day, allowing them to collect high-resolution data. Medium Earth orbit, or MEO, located at an altitude of 5,000 to 20,000 kilometers. Satellites like GPS use this orbit for navigation. They have a longer orbital period compared to LEO satellites. Geostationary orbit, or GEO, located at 35,786 kilometers. Satellites in this orbit stay in the same position above the Earth, which allows for constant communication and weather monitoring. Sun-synchronous orbit, SSO, passes over the polar regions at an altitude of 600 to 800 kilometers. Satellites in this orbit always cross the same point at the same local solar time, making it useful for Earth observation. Geostationary transfer orbit, or GEO, used to move satellites from a transfer orbit to a geostationary orbit. Satellites do not always reach their final orbit immediately, and GEO helps them reach to desired position with fewer resources. All Earth observation satellites have a sensor pointed toward Earth, but their structure and function vary. The most popular has an electro-optical sensor which makes the satellites function much like a flying camera. Google Maps and many defense applications rely on this technology. These passive satellites detect radiation reflected off Earth's surface, like visible light and infrared. They are not effective at recording through clouds. By contrast, active satellites transmit energy toward Earth, then measure the returning signal to gather information about the Earth's surface. In general, active satellites can see through clouds. A common active satellite uses synthetic aperture radar to see through clouds, dust, and darkness, giving it the ability to provide around-the-clock information. Satellites equipped with multispectral and hyperspectral imagery can detect detailed information for farming and other operations. Using specific bands, these satellites can detect crop moisture in soil, plastic pollution in oceans, track commodities, assess natural and man-made disasters. Earth observation satellites are typically found in low Earth orbit, about 500 to 1,300 kilometers above Earth. This orbit works best because the closer the photo, the higher the resolution and the better the quality. Some satellites move in a geosynchronous orbit, but only a few. Most satellites use a sun-synchronous orbit. In this orbit, satellites fly over the Earth's policies and are always in the same position relative to the Sun. This allows them to pass over the same area at the same time every day. This is useful because the satellite can watch changes over time. Satellites in sun-synchronous orbit can also reduce shadows to take clear pictures of the observing area. Let's discuss spectral bands of the Landsat satellites. They represent specific ranges of wavelengths in the electromagnetic spectrum used to gather information about the Earth's surface. Each band is tuned to a particular range of wavelengths, allowing for the detection of various characteristics of objects, such as vegetation, water, soil and their changes over time. A band is a range of wavelengths in which the satellite can capture electromagnetic radiation. Different bands allow for the analysis of unique aspects of the Earth's surface, as different materials reflected and emit light differently. For example, blue band, band 2, used for analyzing water bodies and vegetation, helps identify various types of land cover. Green band, band 3, assess plant health and density, important for monitoring ecosystems. Red band, band 4, useful for detecting changes in vegetation condition and land cover. Near-infrared range, band 5, widely used for analyzing plant health, helps differentiate vegetation from soil and water. Shortwave infrared range, band 6 and 7, useful for assessing soil moisture, vegetation condition, and study minerals. Thermal infrared range, band 10, used for monitoring land surface temperature, which allows for analyzing climate change and ecosystem health. This slide represents examples of different composites created from combinations of different bands. For example, True Color combines red, green, and blue bands, providing an image close to how we see the Earth. False Color uses near-infrared instead of the red band, allowing for better differentiation of vegetation. Healthy vegetation appears in bright shadows of red, while water bodies and other surface display various color. Color infrared combines red, near-infrared, and green bands used for analyzing vegetation health and identifying problematic areas. Using various bands and composites helps to study and display of Earth's surface data, which is important for environmental monitoring, agricultural assessment, and other applications. Satellite imagery data, which contain information from various parts of the electromagnetic spectrum, provide critical insights into vegetation health, soil condition, and water bodies. For example, a combination of near-infrared red and green bands is often used to study vegetation health, assess its density, and determine the overall vitality. In the visible spectrum, healthy vegetation absorbs red light for photosynthesis and reflects little of it, while in the near-infrared spectrum, it reflects much more light. This behavior forms the basis of vegetation indices, such as the normalized difference vegetation index, NDVI, which is designed to monitor vegetation changes over large areas, assess the effects of drought and other natural phenomena. NDVI is calculated using the difference between reflected infrared and red radiation, normalized to indicate the vegetation health across landscapes. The higher the NDVI value, the healthier the vegetation. NDVI is widely used in agriculture to monitor crop conditions. It helps evaluate crop density and health, detect irrigation or disease issues, and even predict yields. NDVI allows farmers to monitor their land effectively, helping them make timely decisions based on real-time crop conditions. The normalized difference vegetation index produces values ranging from -1 to +1, whereas the value corresponds to the type and health of the surface being observed. NDVI values close to 0 or slight negative are common for water, as water absorbs most wavelengths and reflects very little infrared or visible light. Bare soil and deserts usually show DVI values from 0.1 to 0.2 because soil reflects a moderate amount of both red and near-infrared light, but lacks the distinct contrast seen in vegetation. Urban areas typically have values ranging from 0 to 0.2, as built-up surfaces like buildings and roads reflect similarly across the red and near-infrared bands, showing minimal variation. Sparse vegetation or dry areas often have NDVI values ranging between 0.2 and 0.5, indicating areas with little to moderate vegetation coverage. Healthy, dense vegetation has value above 0.5, with the healthiest areas such as forests or well-irrigated farmland reaching values up to 0.8 or 0.9. These NDVI values help in separating between different land cover types and monitoring changes in vegetation health, especially in agricultural, forestry, and environmental monitoring.